Hi, welcome to Physics Constraints in Games, Part 1, Constraint Basics. This is part of a series of talks I gave during a Unity Game Dev meetup in Taiwan back in February 2020. This is a re-recording in English. My name is Ming-Lun. I usually go by Alan. My day job is a game programmer at Naughty Dog. During my free time, I like to research game tech, including graphics, physics, and procedural animation. I also like to make game dev tutorials. You can find my past tutorials on my website, alancho.net. I'm also active on GitHub, Twitter, and Patreon. My accounts on all these platforms are all the Alan Cho. You can also find me on LinkedIn under the account Ming-Lun Cho. First off, let's see what we can achieve by the end of this tutorial. Here you can see a cube. One of its corners is constrained to the sphere. So as I move the sphere around, you can see the cube swings around that corner, which is constrained to the sphere. Now, let's move on to the subject of this tutorial, which is constraints. A constraint is a restriction on the state of the world. One form of constraint can be expressed as an expression equals 0. If this expression is a function of position, we call it a position constraint. For instance, if we want to constrain an object's x-coordinate to 0, this is a position constraint. We can also constrain its y-coordinate, or both coordinates, to 0. Enforcing this constraint in code is very simple. You just keep setting x and y to 0 every frame. Sometimes we have an inequality constraint, like c larger than 0. To enforce this constraint, we detect the opposite condition, which is when this constraint is violated, c less than or equal to 0. Then we enforce the equality constraint, c equals 0. When we talk about game physics, many people would probably picture hard objects bouncing around, bouncing against each other, pushing each other around. That's rigid body physics. Constraints are a higher-level concept. We can simulate rigid body physics just using constraints. Basically, rigid body physics is any two objects, they don't interpenetrate. So the constraint here, what we call contact constraint, is that any two rigid bodies, their penetration distance will always be less than 0, so they're always apart. So what if we don't enforce the position constraint? Instead, we enforce the velocity constraint. Every frame, we set the object's linear velocities x and y components to 0. This means the object doesn't move at all. The meaning of enforcing velocity constraint is that we set the velocity to values that will not further violate the position constraint. So when do we want to resolve position constraints? And when do we want to resolve velocity constraints? It depends. If we want to fix position errors immediately every frame, then we resolve position constraints. If we allow some kind of softness to it, we resolve velocity constraints. Also, how to come up with exact numbers to result in the soft look you want is the topic of a later tutorial. Let's look at another example, ground constraint. We want to constrain an object to be always above ground, so its y-coordinate is always larger than 0. When this condition is violated, we enforce the position constraint y equals 0. This makes sense in code. Basically, we say if the object is below ground, we set it back to ground level. As mentioned before, if we differentiate this position constraint with respect to time, we'll get its corresponding velocity constraint, which is vertical velocity equals 0. So if we resolve this constraint instead, that means when an object is below ground, we set its vertical velocity to 0. But this doesn't solve our problem entirely because the object just doesn't move vertically. This means it's not gonna go deeper into the ground, but this also means it's not gonna correct itself to above ground. So we need another way to somehow correct the position error to satisfy the position constraint. The term c, the expression for our position constraint is also the positional error, which tells you how different the current state is away from 0. In the same example, the ground constraint, C is Y, which tells you how deep into the ground the object is. We can feed this error back to fix the vertical velocity. Initially, our velocity constraint is vertical velocity equals 0. Now introduce a magic term, beta over h times the positional positional error, which is y. H is the delta time between frames. Beta is a number between 0 and 1. If we move this entire term to the right of the equation, we can see that if we enforce this as our new velocity constraint, the deeper the object is into the ground, the more positive velocity will be introduced to correct this error. If beta is equal to 0, we have the same case as before. There is no positional error feedback. If beta equals 1, then the next positional integration would correct all the positional error. Any value in between 0 and 1 for beta means the correction will happen over the course of multiple frames. As for the speed of correction and the precise beta for that is the topic of another tutorial. Right now, just treat that as a magic number between 0 and 1. We call this technique bomb guard stabilization. Now that we have the equation, let's look at the code. First, we integrate the velocity using gravity, and then we check if the object is below ground. Then we feed back the positional error, y, using bomb guard stabilization into the velocity. We use the updated velocity to integrate the position. Let's see what it looks like. Right now I'm using a very low beta value, so if the object falls from above, you can see it goes underground and then slowly move back up above ground. If we use a higher beta value, and let's move the ball again, you can see it corrects itself much faster. Now it's time to generalize velocity constraints. A velocity constraint can be generalized as a linear combination of velocity components plus a bias term equals 0. Here is a column vector that contains components of the velocity. On the left is a row matrix that contains coefficients to linearly combine the velocity components. This can also be expressed as jv plus b equals 0. This is the central equation for generalized velocity constraints. J is the Jacobian matrix. I sometimes just call it Jacobian. V is the velocity matrix. B is the bias term. Using the ground constraint example again, let's look at what J and B are. We already know that V is the velocity matrix. Recall this is our equation for velocity constraint. If we compare the terms, we can see that J is 0, 1, and B is the bomb guard stabilization term. Now, let's see how to come up with a generalized solution to resolve violated velocity constraints. Let's denote V1 as the initial velocity which violates the constraint. So if we pass V1 to JV plus B, it's not going to equal to 0. And let's denote V2 as the resolved velocity. So if we pass V2 into JV plus B, it's going to be equal to 0. The change in V necessary to fix this velocity, or fix this velocity constraint, is V2 minus V1. That is the change in velocity. Change in velocity multiplied by m, which is the mass matrix, is equal to the impulse. The impulse necessary to apply to the object to result in the fix of velocity. And let's say this impulse is equal to L times lambda. L is a vector in the direction of the impulse. Lambda is the impulse magnitude. So the problem becomes finding L and lambda. By the way, uppercase M is the mass matrix, and it's equal to a 2x2 matrix. It's only 2x2 here because we're just treating V as a 2D vector. If V's dimension is different, the dimension of the mass matrix will also be different. We'll see that later. The diagonal term of the matrix are all lowercase m's, and lowercase m is the mass of the object. Non-diagonal terms are all zeros. Here I'm just going to say L is equal to JT, which is the transpose of the Jacobian matrix. As for Y, I will explain it later. So let's just move on to finding lambda, knowing that L equals to JT. So if we move things around from the second equation, we can end up with an expression for V2 in terms of V1, the mass matrix, the Jacobian matrix, and lambda. We also know that if we plug this expression back into JV plus B, or plug V2 back, it's going to be equal to 0. So we'll get this. And now we can collect the terms to have an expression which is, or equation which is, something multiplied with lambda equals JV1 plus B negated. This term on the right is basically plugging V1 back into JV plus B and then negate the entire term. So we now have a final expression for lambda, which is negative JV1 plus B divided by J M inverse JT. To recap, JV plus B equals 0 is the generalized form of velocity constraint. If the constraint is violated, which means JV plus B is no longer equal to 0, we need to change V so that JV plus B is equal to 0 again. And the amount to change V to fix this constraint is delta V, which equals to V2 minus V1, which is equal to M inverse times J transpose times lambda. And I just realized I should have said J transpose earlier instead of JT. And the expression for lambda is negative JV1 plus B divided by J M inverse J transpose. Usually we would collect the numerator term for lambda into a separate term called the effective mass, which is the inverse of J M inverse J transpose. So lambda can be expressed as the effective mass multiplied by negative JV1 plus B. Lambda is known as the Lagrange multiplier. Earlier I said L, the direction of corrective impulse, is equal to J transpose. Why is that? Why is the impulse necessary to correct a velocity that violates the velocity constraint? Why is it parallel to the Jacobian matrix? Let's come back to JV plus B equal to 0. If V is a 3D vector, this equation is a linear combination of the three components in the velocity vector plus a scalar, which is a bias term, equal to 0. This can be expanded into this form: AX plus BY plus CZ plus D equals 0. And this is a plane equation. Imagine this. A point on the plane means this point satisfies a constraint. If the point is off the plane, that means this constraint is not satisfied. So if we want to move a point back onto a plane, the shortest way, or the best direction to move the point is along the plane's normal, which is the coefficient of linear combination of x, y, and z. And that happens to be the numbers inside the Jacobian matrix. And that is why the impulse is parallel, the best impulse to fix velocity is parallel to J. With this plane analogy, we can picture geometrically how to solve two velocity constraints. So C1 equals 0 and C2 equals 0 are two constraints in the world, and that black dot over there represents the current state of the world. To solve C1, we project the dot onto C1 equals 0, and then to solve C2, we project the result on C1 equals 0 to C2 equals 0, and then we perform this projection back and forth iteratively. With enough iterations, we will converge at a global solution, a global state that satisfies both constraints. Back to the ground constraint example. Now we're going to use the generalized approach to solve a violated ground constraint. Here's our generalized form, jv plus b equals 0. And here's our velocity constraint from before. And let's match some terms. So the Jacobian is 0, 1. The bias term is the Baumgarten stabilization term. Lambda is equal to this guy on the right. So we can plug this back and solve for the necessary change in velocity to resolve a violated ground constraint, which matches what we derived before. Sometimes we don't want to solve multiple constraints iteratively, like we did in the previous analogy where we project a point back and forth between two planes. For example, point constraints. If we want to pin a point on an object to a point on another object, this is going to involve a position constraint and a rotation constraint. Solving one constraint after another, the later one is going to take precedence or priority, which means if I solve the rotation constraint last, it might violate other constraints slightly. So ideally, we want to solve both the position constraint and the rotation constraint at once, in one go. How do we do that? Let's look at these two constraints. J1v plus b1 equals 0, and J2v plus b2 equals 0. We're going to collect the separate Jacobians and the separate Baz terms into our general form, jv plus b equals 0. In this case, J is J1 and J2 stacked together, so J is no longer a row matrix. J1 and J2 are individually a row matrix. J is now a matrix with two rows. Similarly, now the Baz term is B1 stacked with B2, so it's a 2D vector, 2D column vector. Previously, I cheated a little bit. I said this is the expression for lambda. Actually, if you look at J, now J is no longer a row matrix. So J M inverse J transpose is not going to be a scalar anymore. It's going to be a matrix. The proper expression for lambda is actually this. It's the inverse of J times negative JV plus B. And the expression for the rest of the other terms will remain the same. And in your own time, you can verify that the matrix dimensions and the vector dimensions all match. So these equations still hold. We now have the expression to solve multiple constraints in one go. Now let's look at another example, point constraint, but without rotation. So just the translational part. We want to constrain an object's position to a point in space, px, py. This is the equation for velocity constraint. And if we differentiate this with respect to time, we'll get its corresponding velocity constraint. This makes sense. Velocity equals to 0. That means the object will not move further away from the point. So it does not further violate the position constraint. And now we're going to do some term matching. General form is jv plus b equals 0. And the Jacobian is the identity matrix here. And the bias term is the Baumgarten stabilization term using the position error as feedback. And let's move everything on the right to the left. We have the formula for lambda. We also have the formula for v2, which is the new velocity. Finally, we can compute the equation or expression for the necessary change in velocity to fix a violated point constraint, which is this. This is basically Baumgart stabilization with the positional error feedback. Now that we have the equation, let's look at the code. C is the positional error. We feed the error back using Baumgart stabilization to fix the velocity. And then we apply a magic number. This is for damping the value so things don't explode. In a later tutorial, I'm going to cover how to come up with precise damping numbers. But for now, just use this magic number. And then we use the updated velocity to integrate the position. And this is what it looks like. Here, I move the sphere around, and you can see the box lags behind to follow the sphere. This is using a low beta value. If I change it from 0.01 to 0.05, you can see that the box springs around faster and closes the gap between itself and the sphere faster. Remember that I will cover how to come up with precise beta values to achieve the desired effects in a later tutorial. So far, we've only been using the linear part of position and rotation. Now we're going to also look at the angular part. So in 2D, the position vector, the linear part is the x and y component. Now we're going to include a third component, which is the angular or rotation angle in 2D. Similarly, we're going to expand our velocity vector to include an angular term, which is the angular velocity omega. Also, we're going to expand our 2x2 mass matrix to include a third diagonal term, which is I, the moment of inertia. Think of it as angular mass, how hard it is to rotate an object. Even with all these changes, conveniently, all the formula we derived so far, they all remain the same. Here's another example, rotation constraint. We want to constrain an object's rotation to an angle, theta. This is going to be very similar to the 2D point constraint without rotation. So I'm just going to blow through this really quickly. We have our position constraint, differentiated. We get a velocity constraint, omega equals 0. And we do some term matching. The Jacobian is 0, 0, 1, because there's no linear term. And the bias term is Baumgart stabilization. Move everything on the right to the left. This is our formula for lambda, formula for V2. And finally, we have the equation or expression for the necessary change in velocity vector to fix a violated rotation constraint. Here. Now comes the fun part, 3D constraints. In 3D, there are 3 components in a linear velocity, and then 3 components in an angular velocity. So the velocity matrix now would contain a number of 6 elements, 3 linear and 3 angular. An angular vector in 3D, its direction represents the object's rotational axis, and its magnitude is the rotational speed. The mass matrix is now expanded to a 6x6 matrix. The upper left part is a 3x3 diagonal matrix, where the diagonal terms are all equal to the mass of the object. This 3x3 matrix corresponds to the linear term in the velocity vector. And the bottom right part of the mass matrix is a 3x3 inertia tensor. Moments of inertia in 3D are represented using 3x3 matrices. Differently shaped objects would have different inertia tensors. And for inertia tensors for common shapes, you can look it up on Wikipedia. And the inverse mass matrix is simple. You just take the reciprocal of the mass terms on the upper left, and then just invert the 3x3 inertia tensor on the bottom right. Now it's time for the final example of this tutorial, which is the one we saw at the very beginning. It's the point constraint plus rotation. Remember, we have a cube where one of its corners is constrained to the center of a sphere. Now let's define some notations. The center or the position of the cube is x, and the vector from the center of the cube to one of its corners is r. And then the point we want to constrain that point on the cube to in space is p. So the position constraint is x plus r minus p equals 0. And afterwards, I'm not going to read everything because there's a lot. So if you need time to catch up, feel free to pause the video. Now we differentiate the position constraint with respect to time to get the velocity constraint c dot equals 0. This is basically the effective linear velocity of that one corner on the cube under the effect of linear and angular velocity from the cube. And the same drill as before, we do some term matching to find J and B. J is a 3x6 matrix, the left half is an identity matrix, and the right half is a skew matrix that corresponds to a cross product with the R vector. And now we're going to collect all the known equations and leave them on the left. This is the formula for lambda, which is equal to this big guy. And you can perform some cancellation here and we'll end up with this expression. And finally, we have our delta V equal to this guy. Now it's time for code. Here is the position constraint, which is also the positional error. And here's the raw velocity constraint, which is the velocity error. And here's the bias term, which is the Baumgart stabilization term using the positional error as a feedback. And then lambda. Using lambda, we now have the correction in velocity to satisfy the constraint again. And we use the updated velocity to integrate the position. And here's the example again. Quite fancy. If you want to build a constraint engine, here's an example update loop. First, integrate velocity using things like gravity. And then collect and generate violated constraints. Next, solve the constraints by iterating over them multiple times. And then using the fixed velocity to integrate position. And if you have any position constraints you absolutely want satisfied at all times, now is the time to do it. Iterate through all the position constraints, resolve them multiple times. And there you have it, an example update loop. Lastly, here's a summary of this tutorial. We see that we can express a position constraint in the form of c equals 0. And if we differentiate this expression with respect to t, time, we'll get c dot equals 0. This is the velocity constraint. And the general form of velocity constraint is jv plus b equals 0. And one use of the bias term b we saw in this tutorial is Baumgart stabilization, using the positional error as a feedback. And here's the expression or formula for effective mass. Here's the formula for lambda, which is the impulse magnitude required to fix a violated velocity constraint. And here is the change in velocity in order to correct the velocity so that the velocity constraint is satisfied again. That's it. Thank you for watching. The slides, examples, and source files for this tutorial are all available on GitHub. If you like this tutorial, please consider supporting me on Patreon. Thanks.